Helicopter Flying Handbook 4.3 Helicopter Components Sections and Systems. Welcome to the heart of the helicopter, the fuel system. Picture it like a complex but essential network with two key players, the supply and control components. Let's start with the fuel supply system, represented by the dynamic duo of tanks, gauges, valves, filters, and pumps, forming a ballet of precision in your helicopter's belly. This visual showcases a typical gravity-feed fuel system in a reciprocating engine helicopter, revealing its vital components. The fuel tanks are strategically positioned near the aircraft's center of gravity. As the fuel depletes during flight, the impact on the center of gravity remains minimal. To maintain the fuel's purity, a drain valve at the tank's bottom helps pilots eliminate water and sediment. The fuel vent prevents vacuum formation, and an overflow drain safeguards against tank rupture. Fuel embarks on its journey through a shut-off valve, a crucial guardian capable of halting the fuel flow in emergencies or fires. During standard operations, this valve remains wide open, ensuring a smooth flow. In the realm of non-gravity feed systems, both electric and mechanical pumps come into play. The mechanical engine-driven pump takes the spotlight as the primary force behind fuel delivery to the engine during its every heartbeat. Fuel filters act as vigilant gatekeepers, eliminating moisture and sediment from the fuel before it reaches the engine. These impurities tend to settle at the bottom of the filter sump, awaiting the pilot's command to drain them out. Enter the primer, a little manual vapor pump or MVP helping in cold weather. A manual pump allowing direct fuel injection into the cylinder intake port before starting the engine, overcoming the challenges of cold fuel vaporization. Now, take a glance at the pilot's instrument panel featuring a fuel quantity gauge. This gauge, a faithful informant, displays the amount of fuel in gallons or pounds, ideally accurate when the tank is near empty. Remember, as per the Aviation Gospel, 14 CFR Section 27.1337, B.1, fuel quantity indicators should read 0 during level flight when only unusable fuel remains. This ensures a safety net, much like your car's gas gauge reading empty when there's a reserve. For the modern helicopter, the comprehensive fuel supply system, ready to support your aerial adventures. Always be fuel-wise, as 14 CFR Section 27.1305, L.1, demands a warning system for approximately 10 minutes of usable fuel. Fuel planning is key, preventing unexpected challenges with fuel levels mid-flight. So, before soaring into the skies, make sure your helicopter is fueled up, and enjoy the freedom of flight without fuel-related worries. Let's delve into the intricate workings of helicopter engines and explore the meticulous coordination of the engine fuel control system. Whether it's a reciprocating engine or a turbine engine, both derive their power from the ignition and combustion of the fuel or air mixture. Visualize this system as a conductor orchestrating several components to precisely meter the right amount of fuel needed for optimal power production. Now, let's discuss a phenomenon that can significantly impact your helicopter's performance: carburetor ice. This sneaky adversary strikes when vaporization and reduced air pressure in the carburetor cause a sudden drop in air temperature. If moisture is present, it can condense, forming ice inside the carburetor. This chilling scenario poses a serious risk of engine failure, especially when using reduced power during descent. Signs of carburetor icing include a drop in engine RPM or manifold pressure, an abnormal reading on the carburetor air temperature gauge, and engine roughness. When activated, it blocks normal airflow, diverting heated air from an alternate source like the exhaust manifold to melt away the ice before it reaches the carburetor. This life-saving move is depicted in this visual carburetor heat system. Pilots should consult their rotorcraft flight manual or RFM for specific procedures on when and how to apply carburetor heat. Now, let's shift gears to fuel injection. In this system, fuel and air meet at the fuel control unit but stay separate until reaching the cylinder's intake port. The fuel is injected directly into the port, mingling with air just before entering the cylinder. This approach ensures a more uniform fuel distribution among cylinders and enhances vaporization, leading to a more efficient fuel utilization. A notable advantage of fuel injection is its immunity to carburetor icing, eliminating the need for a carburetor heat system. As you navigate the skies, understanding these fuel control systems becomes vital. Whether you're dealing with carburetor heat to melt away the ice or reveling in the efficiency of fuel injection, each component plays a crucial role in keeping your helicopter in harmony with the air. Remember, a well-informed pilot is the true captain of the skies. Now, Let's illuminate the intricacies of helicopter electrical systems as we embark on a journey through the marvels of modern avionics. In the realm of helicopters, electrical systems have evolved to accommodate sophisticated avionics and a plethora of electrical accessories. In today's flight environment, the aircraft's electrical system plays a pivotal role, although rest assured, helicopters can be skillfully flown even in the absence of electrical power during malfunctions or emergencies. Helicopters typically house either a 14 or 28-volt, direct current electrical system. Small, piston-powered helicopters rely on an engine-driven alternator, utilizing a belt and pulley system akin to automobiles. These alternators, unlike their predecessors, boast lighter weights, reduced maintenance needs, and a consistent electrical output, even at low engine RPM. For their turbine-powered counterparts, a starter or generator system takes center stage. Permanently coupled to the accessory gearbox, it draws electrical power from the battery during engine startup. Once the engine roars to life, the starter or generator seamlessly transitions into its role as a generator. Picture the current flowing from the alternator or generator, regulated by a voltage regulator, ensuring a constant voltage supply to the electrical system. An over-voltage control acts as a safeguard against excessive voltage that could harm electrical components. This current is then channeled through a bus bar, acting as a distribution hub for various electrical components. Primarily serving to kickstart the engine, it also permits limited operation of electrical components, such as radios and lights, without the engine running. In the event of alternator or generator failure, the battery transforms into a vital source of standby or emergency electrical power. Keeping a vigilant eye on the system's health is the ammeter or load meter, monitoring electrical current flow within the system. A charging ammeter signals that the battery is replenishing its power after engine startup. An ammeter showing a discharge indicates that the electrical load surpasses the alternator or generator output, with the battery lending a hand. Navigating this electrical symphony are electrical switches, facilitating the selection of electrical components. For components requiring high current, relays come into play, serving as intermediaries between switches and power-hungry components. To safeguard against overload, circuit breakers or fuses stand guard, popping out when a component is overloaded. A reset may be attempted, but if the overload persists, it's a telltale sign of an electrical malfunction. The pilot is alerted to such malfunctions through caution lights on the instrument panel. As we delve into the realm of hydraulics, envision a robust system designed to conquer high control forces in helicopters, especially in larger turbine-powered models. This visual provides a glimpse into a typical hydraulic system in light to medium-range helicopters. This hydraulic marvel comprises actuators or servos on each flight control, a pump typically driven by the main rotor transmission, and a reservoir for hydraulic fluid. Some helicopters incorporate accumulators on the pressure side of the hydraulic system, ensuring a continuous fluid pressure supply. A fail-safe system is in place, allowing the pilot to maintain control even if electrical power is lost mid-flight. The pressure indicator in the cockpit serves as a vigilant guardian, keeping tabs on the hydraulic system's well-being. Picture making a control input, and the servo leaps into action, providing an assisting force to move the respective flight control. This hydraulic ballet dramatically reduces the force the pilot must exert, translating into eased workload and diminished fatigue. In the unfortunate event of a hydraulic system failure, the pilot retains control, albeit with substantially heavier control forces. In helicopters where control forces are so formidable that hydraulic assistance is imperative, multiple independent hydraulic systems may be installed. For added resilience, some helicopters leverage hydraulic accumulators to store pressure for emergencies, ensuring continued control for a brief duration following a hydraulic pump failure. This grace period offers ample time for a safe landing. As we conclude this enlightening journey through electrical systems and hydraulics, remember, these intricate systems are the silent architects of a helicopter's performance, orchestrating a symphony of control and power. Fly with confidence, guided by the seamless coordination of these engineering marvels.